Hello participants, welcome to lecture 34 of micro irrigation engineering subject. Lecture 34 is on demonstration of irrigation components and evaluation of drip emitters. In previous lecture, we discussed about different components, we discussed about the performance, how they work theoretically, and then we discussed about the fertigation unit, we discussed about different types of filters, how to install all these units in the field, and then how to maintain them. Now, having installed in the field, we need to know whether my drip system is working satisfactorily. So, evaluation is a very important component of the micro irrigation system, whether they are functioning in the field, or second part when the set of drippers after the manufacturing, they should be collected and tested in the laboratory condition before they are installed in the field. That this way also we can understand that whether they are really. So, random samples of 25 means from the lot, and that should be collected, and then they should be, their performance should be evaluated in the laboratory condition. So, here in this particular lecture, we are discussing the demonstration of these components, and then how the and what are the different parameters through which the performance evaluation of drip emitters that can be done. So, when we talk of drip irrigation component, we already discussed, but I am just refreshing you by giving this thing that a drip irrigation system consists of control head unit and then distribution network. So, control head unit involves pump or overhead tank. If it is a small area of few hundred square meter, then overhead tank is sufficient, and because number of drippers and the size of the irrigation plot will be small. So, accordingly the overhead tank can be used, and pump is used to provide, means overhead tank or pump, it is used to provide the adequate pressure head in the pipeline. So, that the water can easily flow through the drip emission devices. Then bypass system is also one of the components. When the water is excess, it is being pumped by the the pump, then the part of this water it can be diverted for to so that the adequate quantity of water it can go to the system. Then fertilizer or chemical injection unit, as the names it says that it is applicator. So, this device and is used to apply fertilizer or chemical or nutrients along with the irrigation water. Pressure gauge is to monitor the pressure in the pipeline, and then sand filter, screen filter, and then gate valve. These are the other devices which are put up under the control head unit. Then under the distribution network, as the name said that distribution means water distribution. So, by using the pipe sizes, these pipe sizes are of different sizes, and when we say the large pipe diameter, that is a main pipeline, and then this is the characteristic. Normally, these are of when the area is very large, then large diameter pipeline is used, or if it is a smaller area 50 millimeter is the size. And then depending on the size of the pipeline and also the amount of water it is handling, then the it should be the pressure range, that is from 4 to 6 kg per square centimeter. Sub main pipeline receives water from the main pipeline, and the size ranges from the 1.5 inch to 3 inch in size, and then it should be withstand the pressure range of 2 to 5 kg per square centimeter. Then ball valve, flush valve, and then these are the other devices which are used to regulate the flow or remove the dirt deposited in the pipeline by using the flush valve. And lateral pipeline, it is these are also of different sizes. In fact, this could be 10 millimeter, 12 millimeter, 16 millimeter, 20 millimeter. These are the different sizes, and then these pipelines are made up of low density polyethylene or linear low density polyethylene. That is this is the plastic material which is used for manufacturing of the lateral pipeline. Emission devices are attached with the lateral pipeline, and depending upon the requirement, a particular type of emission devices such as dripper, micro sprinkler, micro jet, these are of different the discharges, and these are used as per the requirement. Control head unit of drip irrigation is being shown over here. Water is taken from the deep tube well. In this deep tube well, a submersible pump is attached over there. So, in this submersible pump, this is the delivery end of the pump, then water is being taken into the system. Now, the water will come. So, this particular unit where the water is being raised by using an elbow. So, this is the supply end, and at the supply end you see this place is the pressure gauge. This is the inlet end of the gravel filter, where at inlet end we have attach one pressure gauge, and then in this pressure gauge in this particular sand filter, sand is of different grades have been filled in. So, water passes from this filter, it goes to the layer, and then at the downstream end you can see this is the outlet end of the sand filter. So, water passes through the this particular material, and then filtered water it enters to the system, then it comes to this end. So, these two ends, one is the inlet end pressure gauge is attached, at this end pressure gauge is attached. The difference in the pressure head gives that how much is the pressure difference it has caused, whether sand is blocked by the impurities available in the water. Then it comes to the, this is a gate valve where we can regulate the flow, and then this part is having a Venturi injector. This Venturi injector is for injecting the chemical, nutrient or fertilizer which is soluble in water, is supplied to the system. Then we come to the this is a screen filter. So, water will pass through the screen filter, then it goes to the pipeline, and then here there is a arrangement where one can measure what is the volume of water. What is the volume of water it is passing through the this particular pipeline. So, in a given time the volume of water which passes is measured. So, here there is a counter, one can see in this counter there are different the graduation which has been made, where it can be monitored, and then the water goes to the main pipeline. From this place onward the water is supplied to the field, where the network of the sub main pipeline and lateral pipelines are attached. I am going to present here performance evaluation of drip emitters. When the drips emitters are being manufactured. So, from the lot, as I told you that the randomly from the lot the samples are collected, and these samples could be the order of 25, 10 to 25 in numbers, and then by using a test bench by using a test bench their performance is evaluated. So, here in our laboratory condition we have made our own the hydraulic test bench. It is of course is very small in size, that is 3 meter long, and in this test bench a 3 meter long the lateral pipeline is attached, and then there is a provision in this test bench that one can change the slope. So, slope can be made up the hill or down the hill. So, here provision is there that we can change slope up to this is 3 meter long. So, there is a 30 centimeter drop. So, 10% slope means we can vary the slope 2.5% or 2%, 4%, like this 6%, 8% and 10%, and then see whether how much discharge variation takes place in the drip through the drip emitters for the different pressures. So, water is supplied from the inlet by using the pump, and then the water is supplied in the lateral pipeline from the upstream end or inlet end, and then means adequate pressure, required pressure, because we want to establish some certain relationship. So, pressure is created. So, this pressure could be in the order of 0.2, 0.4, 0.5, 0.6, 0.8 means how these drippers they are performing at different pressures. Of course, ideal pressure to operate these are 1 kg per square centimeter, but there could be different situations where that much of pressure may not be available, or pressure is available at higher rate. Then one can use these pressures and know that how much the discharge variation it takes place by changing the pressure due to change in the pressure rate. And normally pressure compensating of drippers, these types of drippers they are majority of the drippers are non pressure compensating type they are attached with the lateral pipeline, and then the different pressures are changed. So, change in then means for a given slope the observation is taken, then we will change the slope and then take the discharge values. So, discharge value is calculated by taking the volume of water for a given time. So, discharge is calculated. So, this is a hydraulic test bench which you see here, the pipeline in which the lateral pipe is attached, and in the lateral pipe these are the drippers which have been shown in the figure. It is and then the water is being collected by measuring cylinder, and then the volume of water which is collected in a given time. So, discharge is estimated. So, here and then there is a provision that we can change the position, we can change the position of the lateral line, and then the when we are changing the position, say we are bringing here and this is the position. So, this will be when the water is being supplied from one end. So, water will go from this end to the other end. So, it will be up the slope, or you are keeping it here and then the bringing this particular downstream end of the pipeline to this position. So, it will be that it was the up the slope and this is the down the slope, and then discharge values are estimated. So, there when we want to evaluate drip emitters, so this evaluation is done by using some certain parameters. So, one of the parameter is manufacturing characteristics, means when the drippers are manufactured, there can be this is a heating process, and then the polymer is the means material. So, there could be because of the heat or difference in the temperature. So, there could be malfunctioning of some certain component, and you may find that the some of the drippers they are not falling in the correct category. So, here it is means it is based on the, so the discharge is estimated, and from the given discharges we want to find out the coefficient of discharge. So, coefficient of discharge is known as a manufacturing coefficient of variation, means the coefficient of variation is estimated as the standard deviation divided by average flow rate. Now, having got the value of CV, that is so American Society of Agricultural Engineers in 1989, they have recommended that if it is a point source type of dripper and then the coefficient of variation is falling less than 0.05, it is considered as excellent. In case of line source dripper, if it is less than 0.1, it is a good. Like this, excellent, average, marginal or poor are unacceptable. So, if CVM value it is too low, means it is it is a very high value, that is say let us say greater than 0.15, it means these dripper we will have too much of variation, and the basic purpose of using the drip system will be defeated. So, one should reject the lot, that particular lot of the drippers which has been manufactured, this should be rejected and it should not be used for system. That is the way, that is the reason for estimating the manufacturing coefficient of variations. Then there are other parameters are operational characteristics. Operational characteristics means it is basically it is giving that how uniform water is being delivered or by the set of drippers. So, the drippers which were connected in the lateral pipeline in the hydraulic test bench, the data are being collected, and from that data the emission uniformity is one of the parameter which is estimated. So, we means this emission uniformity EU is given by Q n by Q a. What is Q n? Q n is the average of the lowest 1/4 of emitter flow rate. Let us say and then Q a is the average flow rate. So, let us say that suppose we have got 24 number of drippers. So, 1/4 means data will be all 24 data will be arranged either in descending or ascending order of the magnitude. So, suppose if it is a descending order of the magnitude. So, last 6 dripper discharges will be used to for calculating the emission uniformity. So, last 6 means 1/4 will be 6 drippers. So, last 6 means that is a lower order. So, 6 average of this last 6 dripper, that is a Q n, and Q a is the average of 24 number of drippers, that will be the average flow rate, and then this value will be used to calculate the emission uniformity. Absolute uniformity is the another parameter. Here it is given as a half Q n by Q a plus Q a by Q x. So, this Q n already I have explained, Q a I have explained, and then Q x is the average of highest 1/8 of the emitter flow rate. So, I was telling about 24 number of drippers. So, in case of 1/8 become 3 drippers. So, top 24 drippers discharges will be used to find out the average of the highest 1/8 of the flow rate, and then that will be that is the Q x, and remaining values will be same as that is Q n by Q a, and then already you know the Q a, that is the average of 24 number of drippers, and then we will find out the absolute emission uniformity. This absolute uniform as the name is given, that it is the value which will be giving us that how the variation is taken. Then percentage difference, that someone wants to know that how much variation in the discharge take place. So, Q r minus Q a divided by Q r multiplied by 100, where Q r is the nominal flow rate. So, nominal flow rate is the discharge of the design specified by the manufacturer. Say it is a 8 liter per hour dripper. So, and Q, so this Q r is the say 8 liter per hour, and then average value of 24 number of dripper divided by the nominal flow rate, that is 8 liter per hour divided multiplied by 100. So, if you are taking 8 liter per hour drippers, from there you are finding out how much is the percentage variation it is there, that way it will be obtained by using. Then the another parameter of evaluation is hydraulic characteristics. So, hydraulic characteristic is evaluated by using the flow rate, that is Q equal to coefficient of discharge multiplied by the operating pressure to the power exponent x. Now, exponent x value which we will get by using, because you are monitoring the discharge for the different operating pressures. So, Q is known to us, means suppose there are, as I told, there are 24 number of drippers. From the 24, so there will be 24 Q's and for the from the 24 operating pressures. So, from those values you will be getting the value of coefficient of discharge, and then means you will plot the data, and then you will get the value of x. So, x is obtained by plotting these data either in the log sheet, or you are using set of equations to find out the value of C d and x, and then x defines the what type of emitter it is, what is the type of emitter and under which flow regime it is there. So, these are the parameters. Suppose when we say the x equal to 0, x equal to 0 means Q equal to C d. It is simply Q equal to C d, means irrespective of any change in the pressure, discharge remains same. So, such drippers are categorized as pressure compensating dripper. Such drippers are characterized as a pressure compensating dripper. Now, if x equal to 1, this is the another extreme case. When x equal to 1, such drippers are known as means fully laminar flow, and then this is a capillary, means the water is coming from the capillary tube or diameter is means of the flow. So, there is a not much resistance to flow which takes place, and then if it is a 0.9. So, this is a mostly laminar, and then micro tube is, it is the case that water is flowing there. So, there are different cases. Normally, you will find that the majority of the drip emitters, they fall under the orifice or tortuous path type of dripper, or long or spiral path of drippers. So, you will be getting the set of data, and from those data you are getting the value of say data is here, data are that we are collecting discharges from the given pressure. Say this is the one particular slope, then this is the second, means for this slope what for the different operating pressures, what is the values of the discharges. Then second slope, when we have changed the slope, then you are again collecting, and then this like this, and then from these you are for a given slope you are establishing the relationship between flow rate and the operating pressure, that is and then if you plot these data on the log paper, it should follow a straight line. Then we will evaluate from those data the results. So, results we will get coefficient of variation, which we call it a manufacturing coefficient of variation. We will establish the relationship between flow and discharge. So, this equation will be established. We will find out emission uniformity, absolute emission uniformity in percentage, and then you will interpret the results from the table which already I have given you. So, this particular thing we will be means we are showing you how the data are being collected from hydraulic test bench, and then these data will be analyzed for these parameter from the given set of theoretical formulae which I have explained you. This is a hydraulic test bench for evaluation of drip emitters. This hydraulic test bench is meant for finding out the emission uniformity of drip emitters. So, a pump is used to collect water from the source, then water comes through a set of drip irrigation filters, then it goes to the main pipeline, from main pipeline it goes to the sub main and lateral pipeline. In this particular laboratory experiment, we have kept in the lab, where you can see the water is taken from the source. So, this is a collection tank which is a sump, and in this sump the water is stored, and then the water is pumped. So, this is the suction end of the pump, this side is the delivery end of the pump, and this pump is coupled with a small motor. Then the water is being pumped, it comes to the this delivery end of the pump, and then it goes to the lateral pipeline. So, in this lateral pipeline, this is a lateral pipeline, we have attached drip emitters. There are 10 number of drip emitters which are spaced at 30 centimeter spacing. We will evaluate the performance of these drip emitters. Now, performance, it means that we want to see how the water is getting distributed, or it is passing when so amount of water which is getting distributed in all these drippers. So, how uniform this water is being distributed? We will take the observations in a given time of water dispensing out of these emitters. So, water will be collected with the help of these graduated flask, where you can see here each graduated flask is of 250 milliliter. So, for a given time amount of water which is collected in the collecting flask, and then we will find out how much discharge it is coming out of the drippers. So, one part is to find out the uniformity. So, in the theory class we have explained you different types of emission uniformity. What happened when these drippers are being manufactured? There could be some manufacturing defect. So, there we can also find out manufacturing coefficient of variation. So, we will evaluate from the data collected from this. Then this is a very important aspect, that to classify the dripper under which category it passes through. So, we will be evaluating the pressure discharge relationship. So, this test bench has provision where we are using a pressure gauge, that how much pressure is available at the supply end of the lateral, that is at the inlet end of the lateral, Now, in this test bench one can change the slope, means when the laterals are to be laid up the hill or laterals are coming down the hill. So, in this case up to 10% means this, if you see here, this slot is made so that we can change the slope. So, when we will bring down, it means the lateral will go up the hill. So, up to 10%. So, this particular it is a of 30 centimeter this fall is there, fall in the slope, and then the other end also, if you see here, this end also there is a provision. So, if I put it on the top and then bring the lateral position at this place, that is 30 centimeter down. So, it will be again there will be. So, we can have the gradual variation in the slope, which normally it exists in the field that lateral is placed up the slope or down the slope. So, effect of the slope on the discharge and pressure relationship, this also varies, and how much is the head available at the drip emitter, accordingly the discharge will be coming out of this. So, we are now going to start the test the data which will be collected from these drippers. The operating pressure to supply water in the drip lateral is 1 kg per square centimeter, which is equivalent to 10 meter of water column. We start. Nine ml of water has been collected from the dripper. When we will collect set of these data, from these data we will find out the coefficient of discharge and exponent x. Now, data which were collected, say for 1 kg per square centimeter, the time of observation was 1 minute, and then we have got data. Say there were 10 drippers, and then for these 10 drippers the observations were taken, and these observations were again repeated in order to get this. So, we repeated 3 times. So, volume of water collected from the 10 number of drip emitters were collected for 1 minute at the pressure of 1 kg per square centimeter. Then the pressure was reduced, and then again 3 sets of observation, means 3 times it was repeated for these drippers. So, this is for the another pressure the data were obtained. Then again when the discharge this means your pressure was reduced to 0.5 kg per square centimeter, then volume of water collected from 10 drippers were collected, and then what we will do, we will find out the different parameters which are needed. So, say just I am for example, we calculated because it was for 1 minute. So, we calculated the value of discharge. So, discharge, say you are it is shown here 7.5 liter per hour. So, the average value from the 3 sets of observations, for one particular observation which is being shown. So, this was 125 ml in 1 minute. So, we converted to the liter per hour. So, liter per hour it is coming 7.5 liter per hour. like this, for all the 10 observations data we estimated, and then similarly for the second set of observation, this is for third set of observation, then average value of the discharges from these 10 number of drippers at 1 kg per square centimeter were obtained. So, this average Q A was estimated, and this particular value is what you are seeing here, that is 7.994 liter per hour is the average value. Similarly, the manufacturing coefficient was the formula, if you remember, it is given by standard deviation by mean. So, we calculated the standard deviation. It is a simple formula, x I minus x bar, that is x bar is nothing but Q average, and then divided by n minus 1, and then whole the summation of this value, and then taking the square root of this, that gives the value of standard deviation. So, standard deviation we obtained as 0.2438 liter per hour, and then average was 7.994. So, we got CVM equal to 0.031. We will characterize this particular emitter under which category it falls at later part. Now, coming to the operational characteristics. So, operational characteristics, when we were finding out. So, first we are required to know what is the average lowest 1/4. So, here only 10 numbers of drippers were there. So, we are taking 3 numbers of observations, and then from there 3 observations which are the lowest method. So, we are getting the value as the average of lowest 1/4 is 7.72 liter per hour, and then highest for getting the, if you remember, for getting the absolute uniformity, we are getting 1/8. So, here 1/8 of the dripper. So, we have got only one dripper which is of the highest in the order, that is 8.3 liter per hour. So, emission uniformity is given by the lowest 1/4 ratio of lowest 1/4 to the average value. So, lowest 1/4 we estimated as 7.72 divided by 7.994. This gives the value of 96.57 emission uniformity. It is a very high value, it is a very good acceptable range. Absolute uniformity, emission uniformity. So, this already we got the Q n, we know that this is the value, same value, this is a Q n by Q A. So, 7.72, and then this part, that is a 7.994 is the average value, and then this is the average divided by the highest 1/8. So, this is only one observation, that is 8.3. So, we got 0.9644 or 96.44% is the absolute emission uniformity, and then the percentage difference or deviations, percent deviation when it is being calculated. So, percentage deviation is estimated, that is the Q r minus Q A. So, we take here the absolute value, that is this is the nominal flow rate of the dripper is 8 liter per hour, and this is the average flow rate divided by the nominal flow rate. So, this is coming percentage value is 0.075%. So, very low value. So, this is the then. So, similarly for other discharges, your 0.7 kg per square centimeter we have calculated. Similarly, for 0.5 kg per square centimeter, these values have been estimated, and then we are getting the hydraulic characteristics. So, hydraulic characteristics, if you remember, the discharge Q is related with the operating pressure h to the power x. So, we have been given the pressure head pressure means discharge versus the operating head. So, the this particular graph in fact discharge is depending on discharge is dependent on the operating pressure head. What we will do? We will plot the graph and then we will find out that how what kind of relationship it is there, or simply taking the observation between the h versus x, and from there when we plot it on the log paper, this value h is x is coming at 0.8063 and coefficient of discharge x is 1.25. So, the established equation q, as I told you that it is a function of operating pressure. So, q equal to C D h to the power x. So, C D is 1.25, h is to the power 0.806. This is the equation. Now, by looking this equation as well as from these data, one can make interpretation that the coefficient, this is the result, that manufacturing coefficient of variation CVM is 0.031. So, if you look at the American Society of Agricultural Engineers, that table they have given, that table which already I have shown you, that this particular type of dripper is a point source dripper and the value is 0, it is less than 0.05. So, this falls under the category of excellent. Then the flow rate versus this part, when we are seeing it, that flow rate q and this. So, this establishes the relationship, this one we got, and this is by looking to the value of C D as well as value of x. So, the means the flow regime is mostly turbulent and the dripper is falling under the long path drip emitter. So, that this is the another category based on the value of x which we are getting. Then the emission uniformity, it is because the emitter is performing very under excellent category. So, emission uniformity is of very high order, that is 96.57%, and then the absolute emission uniformity, is the 96.44%. So, if we look at the American Society of Agricultural Engineer 1989 recommendations, they say the emission uniformity of point source emitter, and this particular emitter which we used in our case, this is 30 centimeter spacing, they are giving less than 2 meter category. So, less than 2 meter category spacing and then uniform slope. So, this was under a uniform slope, that is a 0 slope category, we got this value. So, these type of drippers can be recommended for use in the field. Okay, so, these are the references, and then we can summarize that we demonstrated you the different irrigation system component, we evaluated the performance of drip emitters, and then in the forthcoming lecture we will discuss about soil water movement under drip emitter. Thank you very much.